Thank you. So, good morning, everybody. So, let me just begin with thanking the organizers for this invitation and all the arrangements of this online meeting. So, if I am not mistaken, I was the first speaker of the first workshop. I missed the workshop organized by KSOM, and I'm very happy to be part of this event. So, though, of course, I'm missing Kerala. So this is a talk based on an article which you find here, and it's a joint work with Tathagata Banerjee and Manish Kumar. Tathagata Banerjee was my postdoc and Manish is a JRF. And I would like to thank my funding agencies. So let us start. So it is about C-star extreme points of positive operator measures and unital completely positive maps. So this first part, positive operator valued measures, that is abbreviated as POVMs, and unital completely positive maps, abbreviated as UCP maps. Okay, so POVMs and UCP maps. So what are these positive operator valued measures? That is the first thing I will talk about. So then what are these UCP maps? Then how are they related? They are actually very closely connected. So I'll talk about that. And then what is this C-star convexity or the non-commutative convexity which comes into picture? So that is what we are studying mainly with respect to both POVMs and UCP maps. And what are the results we have and some problems also. Okay, so that is the overall scheme. So I'll just start with explaining POVMs and then UCP maps and then see how they are related. Okay, so POVMs are operator valued measures. So you start with the measurable space. So X here is some non-empty set and OX is a sigma field on X. So you have a measurable space and H is some Hilbert space. Okay, so POVM or positive operator valued measure on X is a measure which takes values in positive operators, right? So it's a measure, so it's a map from the sigma field OX to B of H, so that for every set A, every measurable set A, mu of A should be positive in B of H. Okay, so positive in the sense that it is of the kind, so B star B, or you can say it is positive in the sense of quadratic form. Okay, positive as an element of B of H. Okay. So then, so it should be positive and should be a measure. So measure in a very weak sense. So that is, you take any two vectors H and K in H, just look at the matrix entry, mu of A applied on K, inner product with H. So that should be a measure in the usual sense. Okay, complex valued measure, right? Because other Hilbert spaces would be complex and separable. And so mu H comma A is mu of A applied on K, inner product with H. So for every H and K, this should be the usual measure, okay, complex valued measure, okay. And in fact, if you take K equal to H, okay, since mu of A is assumed to be positive for every A, so then this would be a positive measure. If you take H equal to K, then it will be a positive measure, okay. Standard example you may have seen already, namely the spectral measure of any normal operator. So that is a projection valued measure. So in that case, mu of A would be a projection for every A. Okay. So now we are generalizing. Instead of projection valued measures, we are looking at positive operator valued measures. Okay. So POVMs, they are also called generalized measurements in quantum theory, because these spectral measures, they are the usual measurements. For observables, you use the spectral theory or the spectral measure to do the measurements. These are generalized measurements. They also come up in quantum theory and it's very much used. And in fact, you can see a lot of literature, more than mathematics, more in physics about these POVMs. Okay. So that is the basic object of study, our study. So here, for any POV mu, by mu HK, I will mean this complex measure, right? What I wrote here, this the measure which you are getting by looking at matrix entries. And if you know the entries, you know the matrix or the operator. So it's clear that mu is determined by this complex measures mu of hk. Okay. And just a few terminology. So mu is said to be normalized if mu of x is identity. So mu of the whole space is identity operator, then you call it normalized. And it's said to be a projection valued measure if mu of a is a projection for each a. Okay, and it is said to be a spectral measure if mu is a PVM, that is projection valued, and also it is normalized. Mu of the whole space is identity. That is the best situation. That is what you get for self-adjoint operators or normal operators. But this is more general. And sometimes we need some technicalities called regular POVMs. Suppose X is not just a measure space, but is a topological space, and OX is the Borel sigma field, and these measures mu HH are all regular. So regular in the usual sense, that means you can approximate mu of any measure of any set using compact sets from below and from open sets from above, then you call it regular Borel measure. Okay, so that technicality comes sometimes, but I'll mostly ignore it. Okay, I'll mostly talk about these other things. Okay, just say POVM. And then what are these UCP maps? Okay, so take any two unital C-star algebras. So if you are not familiar with C-star algebras, you may think A and B as a continuous space of continuous functions, or the algebra of continuous functions on some compact Hausdorff space. You may also think of A and B as the algebra of bounded operators on some Hilbert space. So one is the commutative case, the continuous functions on some topological space, typically compact Hausdorff space, or bounded operators on some Hilbert space. More generally, I can take subalgebras, norm-closed star subalgebras of bounded operators on some Hilbert space. So they are unital C-star algebras. Okay, so a linear map from A to B is said to be completely positive if phi of a positive operator is positive for every n. So here, so each Aij, each Aij belongs to A. So I am taking matrices with the entries from A. Okay, same way here, and so there is a typo here. It should be phi of Aij. Okay, phi should go inside. So phi of Aij, so that should be positive for every Aij positive. Okay, just a typo. So if you have phi of A positive for A positive, then it is said to be a positive map. Once again, positive, an element A is said to be positive if it is of the kind B star B. Okay, or you can say it is positive if it is a square of a self-adjoint element. Okay, or you can say that A is positive if it is normal and the spectrum is on the positive half line. Okay, for matrices it is same as non-negative definiteness. Okay, that is what is positive. Okay, the quadratic form is positive. Okay. Now here I'm taking entries Aij from A, so these are n cross n matrices. So MNA it also automatically becomes a C-star algebra, n cross n matrices with entries from A. So you apply entry wise. If this is positive, then phi of Aij, there is a typo here, phi should go inside. Phi of Aij, that should be positive. Now, if phi of identity is identity, then you call it unital completely positive map. Now, there is a famous theorem. If the domain or range of positive map is commutative, then the map is automatically completely positive. Okay, so if this map from A to B, if either A or B is a commutative C-star algebra, so it is say continuous functions on some compact Hausdorff space, then I don't have to bother about this n cross n matrices, etc. Just positivity is enough. That will imply that it is completely positive. Okay, it is a result due to Sternspring and Arvesen. And today I will be talking only about CP maps on CX, the continuous functions on compact Hausdorff space. So in this case, just positivity is enough. So you can ignore this definition. you can just say that I'm looking at positive map from C of x to B of h. Okay. So C of x is the algebra of continuous functions on x, x being a compact Hausdorff space. Okay. Okay. So these are UCP maps. So let us now see the connection between the two, the correspondence between POVMs and UCP maps. So this is when x is a compact Hausdorff space and h is a Hilbert space. So then there is a nice connection between regular POVMs and CP maps. So again, regularity I'm just ignoring. It's a technicality. So if you have a measure, okay, POVM, I need to get a CP map and other way around. Okay, so if mu is a measure, a positive operator valued measure. So for any f, mu of f is an operator on B of h. So you just integrate it. So phi mu at f. So I need to define a map for on continuous functions. Okay, so take any continuous function f. Then you just integrate it with respect to this measure mu hk, and you take that as your hkth entry. So that way phi mu at f becomes an operator. So this is the map. Okay, phi mu. So given the POVM mu, you have an operator from C of x to B of h. Namely, given any f, any continuous function f, you just integrate it with respect to these measures, and you get an operator on B of h. And this way, you get a map from C of x to B of h. Okay, and you can see that this measure is a positive operator valued measure that ensures that when f is positive, this integral is also a positive thing. So you get a positive map. Okay. So, and as I said before, once you have positivity, you get complete positivity for free because the domain is a commutative sister algebra. So in the converse direction, if you have a CP map from C of x to B of h, okay, completely positive map or a positive map, then you need to get the POVMs. Okay, so that means you need to get the matrix entries. You just have this f goes to this phi of hk, but then you can see that say if you take k equal to h, then you get a positive linear functional. So then you know positive linear functionals on C of x, they are come by integrals with measures, right? The same thing extended to complex measures. So it's the Rees-Markov representation theorem or Rees representation theorem tells you that these linear functionals have to be integrals with respect to some measures. Okay, you collect those measures, and that determines your POVM. Okay, so one-to-one correspondence. Once you have the measures, you can integrate them, and you can get the maps on continuous functions. And if you have the map on continuous functions, so you getting these operators. Look at the matrix entries. But Rees representation theorem or the Rees-Markov representation theorem gives you the measures. Okay, so that is the correspondence. So throughout the lecture, mostly I will talk only about POVMs and for all the results for POVMs. Then say that the same thing can be transported to CP maps. Okay, so that is the idea. So this way we get this one-to-one correspondence, and we will use this heavily and study just these POVMs. Okay, this is in a sense more general because I don't need X to be compact Hausdorff space, etc. there to talk about POVMs. Whereas to talk about C-star algebras, we need that topology there. Okay, so that's why we will be looking at only on POVMs and then specialize, take X as compact Hausdorff and transform the results to CX and to the CP maps. Okay. So now the notion of convexity and C-star convexity. I believe all of you know what is convexity. So I will just talk about C-star convexity. Okay. So I look at the POVMs on a measurable space. So I'm fixing this X and the sigma field OX, and you fix the Hilbert space H, and P of Hx denotes the collection of all normalized POVMs. Okay. So normalized just means that measure mu on the whole space is identity. Okay. So clearly it's a convex set. So you can ask what are the extreme points of these POVMs. Okay. If you take just the measures, usual convexity, you can ask what are the extreme points. Well, spectral measures are extreme. In fact, you see a proof of that. But there are other extreme points, and there is no explicit description of all the extreme points available. Means there are some results giving you some abstract description or characterizations of extreme points that you will see, but there is no complete description of usual extreme points of these POVMs. That there are extreme points other than spectral measures, even when X is a finite set. Okay, with more than 2 points, I think you will get extreme points other than spectral measures. But our interest today are C-star extreme points. So what are they? So here we take convex combinations where the coefficients themselves become operators. Okay. Suppose we have n POVMs, mu1, mu2, mu_n. So then you take a convex combination like this, Ti star, mu I, Ti, where Ti's are operators. Okay. So you see, if you have a positive operator here, if you conjugate it by any operator, Ti star, some positive operator Ti, that's again positive. Now I can take the sum. So this condition, summation Ti star Ti equal to identity, ensures that mu of the whole space here, if I put the whole space here, you have identity here, you get summation Ti star Ti, which is again identity. So you get another normalized POVM. Okay. So this is called the C-star convex combination. Instead of Ti's being scalars, just numbers, we have operators here. Okay. The usual convex combination, you would have say summation Pi mu I with summation Pi equal to 1. Okay. The same thing has been replaced with summation Ti star Ti equal to identity. Okay. So we call Ti's as C-star coefficients. Okay. If they are just numbers, you would have had the usual convexity. And it's important that when Ti's are invertible, that has a special role. So that we call proper C-star convex combination. Okay. So what are C-star extreme points? Well, this notion of C-star convexity has been around for quite some time. I think Robel and Paulson studied them in 1981, and recently there has been a lot of interest about the C-star convexity, especially because of this, I think, quantum information theory and things like that. Pure Hx, the positive operator valued measures on X, that is a C-star convex set, because if each mu I is POVM, you can see that this is also POVM. Very easy to see. Just to check the positivity, and it's direct. And so what is the definition of C-star extreme points? So we present a definition which is due to Ferencz and Morenz. So they defined it for UCP maps, unital completely positive maps. We transport it to POVMs, and here is the definition. Okay. So a normalized POVM mu is called C-star extreme. Okay, in this collection of normalized POVMs, if whenever you write mu as a proper C-star convex combination, okay, so mu you write as summation Ti star mu I Ti proper, so that means each Ti is invertible. Okay, if you write it that way, each mu I may not be equal to mu, but each mu I should be unitarily equivalent to mu. Okay, so just stare at this definition for some time, because it's very important. This is what we'll be working with all the time. Okay, so you write mu as a C-star convex combination of mu i's, then each of these mu I should be unitarily equivalent to mu. You can see that you cannot demand that each mu I should be equal to mu. That is too much to demand, because you can always modify things for unitaries. So are there any questions about this? Because this is very crucial. We'll be studying just C-star extreme points. So it's important to know the definition. Okay, so I'll go ahead. So we see that spectral measures are C-star extreme. So natural question, like whether that's all. Earlier we said regarding usual convexity, there are other extreme points. Okay, but here we want to show that under good situations, only spectral measures are extreme. So that means using spectral measures, using C-star convexity, then you can get all other POVMs. Okay, that is the thing. So the main result we have is that under good situations, C-star extreme POVMs are spectral. Okay, they are automatically spectral measures, and there are no other C-star extreme POVMs. So it's a sort of basic result characterizing all C-star extreme POVMs. So then it tells you that other POVMs are all just C-star convex combinations of spectral measures. Okay, but there is a catch here, which says under good situations. So good situation 1, for arbitrary x, no conditions, when h is finite dimensional. When h is finite dimensional, nothing to worry. All C-star extreme POVMs are spectral. So this was known when x is compact in Hausdorff. We have the result in general. And the good situation 2, when x is a countable set. Okay, h is infinite dimensional. This was not known when h is infinite dimensional. This was not known even for finite sets. Okay, so now we have the result for countable sets with h infinite dimension. Okay, you ask as to what about general sets? In general, the result it's not true. There are situations, even examples like interval 0 to 1 or the circle with h infinite dimensional. There are extreme points, C-star extreme points, which are not spectral, okay, which are not projection valued. Okay, we will see one example later. There are very natural examples of not pathological or anything, very natural examples for more general situations. So you can't hope too much. So the general situation is still unclear. We don't know as to when exactly there are other extreme points and how to characterize other extreme points. We don't know. Okay, there are some characterization, but no full description. Okay. Okay, so let us begin with the theory now as to what we can prove for POVMs. So here is the basic dilation theorem called Naimark's dilation theorem. Very standard result from 1930s, I think. So you take a POVM. Okay, we assume that we understand spectral measures. So this tells us that the dilation theorem tells us that all POVMs basically come from spectral measures by compressions, by restricting sort of to subspaces or sub. Okay, so all POVMs originate from spectral measures some way. Okay, this is what it's saying. Okay, you take a POVM, then there is a triple pi, v, and h pi. Okay, where h pi is a Hilbert space and pi is a spectral measure. As I said, I want to get this POVM, positive operator valued measure, using spectral measures. Okay, so here is a spectral measure pi on some other Hilbert space, and you have a map v from h to h pi, and your POVM is given by conjugating a spectral measure through some other bounded operator v. Okay, so every POVM comes like this. Okay, and there is something called minimality condition. If the space spanned here in h pi by all action of this pi and v, it will span whole of h pi. Then it's called minimal. So that is, you can take it to be minimal, and then the dilation is unique up to unitary equivalence. I will not explain more what is unitary equivalence, but it's essentially unique. Okay, and this triple pi v h pi is called Naimark dilation triple of mu. If you have studied completely positive maps, this should look very familiar. That there is something which looks like this. Here is another comment, namely that this pi is spectral. Okay, so that means it is always normalized. Okay, pi of whole space is identity. So that means if I put the whole space, mu of whole space, mu of x is just v star v. So mu is normalized if and only if v is an isometry. Okay. So I said before that you may see that this is looks something familiar. So this is the POVM analog of Stein-Spring's representation theorem. For completely positive maps, there is something called Stein-Spring representation theorem, which says that the CP maps can be realized by this kind of conjugation of star homomorphisms. Okay, the spectral measures here would correspond there to star homomorphisms. Okay, So that is Sine-Springs representation theorem. Okay, but we restrict ourselves now for this POVMs. So the summary is here of this theorem is that every POVM comes from spectral measures. Okay, so then there is something which is like Radon-Nikodym type theorem of measures. So you take a POVM and you take another POVM dominated by this. So that means mu minus nu is also a POVM. The difference, you have something new, another POVM, such that mu minus nu is also a POVM. So this is like absolute continuity, but something stronger. In absolute continuity, you just have mu of some set is 0, mu of the same set is 0. But we have a proper inequality here. And the theorem says that anything dominated by mu can be got as mu of A as V star d pi a V, where d is some operator in this B of h pi, which commutes with pi of V. This commutant here just means d belongs to the commutant, just means d commutes with all this pi a. So you can put this d on this side also, and it's a positive operator. Okay, so this d is essentially the Radon-Nikodym derivative, okay, of mu with respect to mu. Okay, and there is a similar theorem for CP maps is because of this correspondence, and the similar theorem for CP maps was proved by Arvesen. This theorem for POVMs, we don't know who proved it. It's there in the literature. Just call it folklore. Okay, so now extreme point criterion. So this is the usual extreme point criteria for POVMs. So you can give a criteria using this minimal Naimark dilation. So a necessary and sufficient criteria for mu to be extreme is that this map D from here P of Hx, the things which are commuting, the Radon-Nikodym derivatives. Okay, so D to V star dV. So that map should be injective. Okay, so this is also well known, and a similar theorem for CP maps was proved by Arvesen. Okay, and this immediately tells you that spectral measures are extreme. Okay, so because when you are having spectral measure, there is no need to dilate. That the original spectral measure, that itself is the dilation. So that means this V is just the identity. So this map is just D going to D, so which is injective. Okay, so every spectral measure is extreme. Now this is the usual extreme point, not the C-star extreme point. For C-star extreme point, there is a similar criteria due to Ferencz and Zhou. Well, they proved it for CP maps. We are presenting the version here, the corresponding version for POVMs. Okay, so mu is a C-star extreme point in POHX if and only if, again, some other condition about the Radon-Nikodym derivatives. So D belongs to this. So it looks a bit complicated. So you may more or less ignore it because I will not use it. And I will use a modification of this. I will not directly use this. So the result of this Ferencz and Zhou, there were some small things which were unclear. We have clarified it, and this is the correct thing. So, and this also tells you immediately that every spectral measure is a C-star extreme point, because in that case, this V is just the identity and everything follows easily. So there is a corollary due to Zhou, or sort of a reformulation of this, which is what we will be using. So let us look at that. So mu is a C-star extreme point in PHX if and only if you take any POVM which is dominated by mu, that mu is less than or equal to mu, so then that mu is given by a conjugation of mu. Okay, so any POVM which is smaller than mu less than or equal to mu, then mu of A has the form T star mu A T. Okay, for some operator T. Okay, for some invertible operator T. So there is a small condition here, mu x being invertible. Okay, so that is crucial. So whenever mu is dominated by mu and mu x is invertible, then I should get a T, such invertible T, so that mu of A equal to T star mu A T. Okay, So that is again necessary and sufficient condition for C star extreme points. Okay, so we have a necessary and sufficient condition characterizing C star extreme points. Only problem is that from that it's difficult to read out as to what are the C star extreme points, what are out there. So we want to show that in good situations they are all spectral measures. Okay, and the spectral measure is C star extreme point is easy, the other way around. Okay, so the crucial step in our proof, our main result is the following. So this is the, you can say in a sense, is the main tool for our theorems. So mu be a C star extreme point in PHX. So if you have a set E such that mu of E commutes with all mu of A, remember this mu of A, these are positive operator valued measures. So these are operators, positive operators. So mu of E should commute with mu of A for every A which is contained in E. Okay, then mu of E is a projection. Okay, so this is a theorem. So I'll give you the idea, main proof of this theorem. That is, this is a crucial result. Okay, so the condition is that this POVM, it's a C star extreme point, and mu of E commutes with all mu of A where A is contained in E. So how will you show that mu of E is a projection? So what we will show is that you take any R and S between 0 and 1, numbers between 0 and 1, you show that the spectrum of mu of E intersected with the interval R to S is empty. And this will show for all R and S. So that means the spectrum of mu of E has no points between R and S for any R and S. So that will show that the spectrum can be only 0 or 1. The spectrum is contained in the set 0 or 1. So that shows that mu of E is a projection. Okay, how do we do that? So we use functional calculus. Okay, so you define function from 0, 1 to 0, 1 this way. Okay, it's a carefully chosen function. So let us look at it. So you fix this R and S, and what is given to us is this mu one set E, where mu of E commutes with mu of A for all A contained in E. Now you fix R and S, you define this function f of t. So this is just 1 outside the interval R to S. And here it is something positive between 0 and 1. Okay. And at R, it is equal to 1. Okay. Put t equal to R, you see that you have got 1. After, so only between R and S, it is different from 1. So at R, it is 1. Then you can see it goes down slowly and goes to some point at S. Okay. So it is continuous except at one point, namely S. Okay. And what is the value at S? This is the value at S. Okay. And that is some number strictly between 0 and 1. Okay. That is what is important. The exact value doesn't matter. It is a number which is strictly positive. Okay. That is important. So f of t is between this alpha and 1. Okay. This number and 1. And it is measurable. Okay. So one of the reasons why we had to do this POVMs is that we are using this measurable functional calculus. We are using this measurable function f. So if you want to do the similar kind of proof using two CP maps, continuous functions, it is not possible. You need measurable functions. That's why this proof works. In the language of POVMs, it doesn't work, at least not in any straightforward way, for CP maps. Okay, because there what you have is the continuous functional calculus. So, but we needed the measurable functional calculus. Okay. Okay, you take this function f. So what do you do with it? So this function takes values between alpha and 1. Okay. So if you take any positive operator, positive contraction t, then I can look at what is f of applied t. So that is an operator between alpha and identity. So crucial thing, f of t is a strictly positive contraction. So that means it is invertible. Okay. So that is what we'll use. So now we define a map nu on OX to B of H. So on the sigma field. this way. So for any set B, it is mu B intersected with B f of mu of E. So I'm using the functional calculus here, and outside E, it is as before. So I'm just changing the measure, the operator measure mu inside E, okay, by this way, okay. So you can see that it is again a positive operator valued measure. So here I need the commutativity of mu at this point and f of mu of E. Okay, this is that f of t, okay, t being mu of E. So this is commutes because of our basic assumption here, this commutativity that ensures that this is commutes and gives you a positive operator. Okay, so you get that this is a POVM, and it is, you can directly check because this is between 0 and 1 that this is dominated by mu. And mu of x is invertible. That invertibility follows from the this fact that f is strictly positive. So this Zeus criteria is applicable. So we have assumed that mu is C star extreme, and we have got a POVM which is dominated by mu. So I can apply Zeus criteria, and you see that mu of B is T star mu B T for every B for some T, okay, from invertible T. So we have to figure out what this T is. So you do the polar decomposition of T. T as some unitary times mod T. Mod T is the square root of T star T. Now T is invertible, so U is actually a unitary, and mod T is, you can compute it by taking here B equal to X. Okay, take B equal to X and evaluate. So you get mu of E here, f of mu of E, and do the computation, and then you just write down what is T star mu of E T. So by using the polar decomposition. Okay, just stare at it. So all I do is evaluate this at 2 points, namely at B equal to X and B equal to E. Okay, so if you evaluate at B equal to E, I get this formula. So mod T, so evaluate at E. Now, okay, so this is the definition I'm using here. So in the summary, what is summary? Mu of E you take as S. So you see that U star SU is some function of S. Okay, S being mu at E. So I want to show that this mu of E is a projection. So I just named it as S. And you see that some function of S is unitarily equivalent to S. Okay. So what is this function? If you do this computation, you see that this function G is given by this. It's a modification of F. Look at the function. It is T. G of T is just T for T outside the interval. So earlier the function was just 1 outside the interval, but it was chosen carefully so that it is just T outside, and inside it is a constant R. Okay. The choice was made so that we get this G. Okay. It is T outside, and f of G of T equal to T for outside the interval and equal to R. Okay, the constant R. So now what do I have? I know that the function of S, okay, S being mu of E, the function of S is unitarily equivalent to S. Okay, so what is the unitary doesn't matter. G of S is unitarily equivalent to S. So that means S and G of S have the same spectrum. Okay, so by the spectral mapping theorem, the S satisfies the spectrum of S is same as spectrum of U star SU, which is spectrum of GS. But G was the function G of T equal to T outside the interval and the constant R inside the interval. So that means the range of G is contained in 0 to R and S to 1. It entirely skips the interval R to S, okay, the range of G. So that means the spectrum of S, since G of S is unitarily equivalent to this, the spectrum of S is contained in 0 to R and S to 1. So which is saying that the intersected with the interval R to S is empty. And this we can do with any R and S. So that means the spectrum of S intersected with the open interval 0 to 1 is empty. So that means the spectrum is contained in 0 or 1. In other words, mu of E is a projection. Okay, so that proves the main step. Okay, and this is what we wanted to show. Okay, so now we see the consequences of this result. Okay, we need the notion of atomic POVMs. A subset mu, subset A is called an atom for mu if mu of A is non-zero, and whenever you take a subset B of subset of A, mu of B is either 0 or equal to mu of A. So then you call it A as an atom. And a POVM is called atomic. Okay, if every A, we don't say that every A should be an atom. Every A with mu of A non-zero contains an atom. Okay, then it's called atomic. Okay, and it is called non-atomic if it has no atom. If every A with mu of A not zero contains an atom, then it is atomic. And if there is no atom, it's called non-atomic. Okay, there is a theorem which says that every POVM decomposes uniquely as a sum of an atomic POVM and a non-atomic POVM. Okay, it's again a well-known theorem. So, and what happens if it is atomic? See, if you have atomic, if you take an atom, anything inside that mu of B is either 0 or the whole thing. So that means you have the commutativity for free. Okay, so our previous theorem is applicable. If you take any A with mu of A not 0, you take any B inside that. Mu of B is either 0 or mu of B equal to mu of A. So that means mu of B always commutes with mu of A. The previous theorem is applicable. So that means mu of A is a projection. So we get this theorem immediately. An atomic normalized POVM mu on a measurable space X is a C star extreme point in PHX if and only if mu is spectral. All we have to show is that mu of any set is a projection, and that is immediate because for all subsets, for whenever you take an atom, whenever every point is has an atom there, so from that you can see that mu at every point, every set is a projection. Okay, so that shows one way. The other way is, anyway, we know that spectral POVMs are C star extreme. So in particular, if X is a countable measure space, so if X is a countable set, then you can see that you have all the singletons there. They're all C star atomic, so they're all projections. So from that you see that PHX is spectral. Okay, so for the countable case follows easily because you have the things to be atomic. So here is the direct sum decomposition of C star extreme points. If you have a C star extreme mu, then you can decompose it. So it follows that you can decompose it as mu1 direct sum mu2, where one is atomic and the other is non-atomic, and they are mutually singular. So you have a direct sum decomposition. Earlier we had just sum, but now direct sum, and such a decomposition is unique. Okay. So more crucially, when this is C star extreme, this mu1, mu2 are C star extreme, and in particular, the atomic part is spectral. Okay. So another result, the commutative POVMs. So here you are assuming commutativity. So let mu from mu OX to BH be a commutative normalized POVM. Then mu is C star extreme if and only if it is a spectral measure. Again, you can see guess the proof, because once you assume commutativity, the crucial result, the main result is applicable. So you get mu of every set as a projection, and that is the result. Okay, so this is clear from the main result. Similar result for instead of C star extreme point for usual extreme points is also true, and that was proved by these people, Hinosari and Peronapa. So for usual C star extreme point, usual extreme points for under commutativity assumption. Okay, so I also claimed the result for finite dimensional Hilbert spaces. So if you have H to be finite dimensional, then any C star extreme point is spectral. So our result is not directly applicable. You have to go slightly roundabout. Firstly, when you have this finite dimensional H, so every C-star extreme point is also extreme. Okay, this was proved by Ferenczi, Fosker, and Smith. So it is automatically extreme. So by the way, this is not something obvious or something which actually something which we don't know whether in general C-star extreme means extreme or other way around. Okay, we don't know that. So we show here in this case, at least when H is finite dimensional, every extreme point is atomic. So once you show that it's atomic, our main result is applicable, and you see that it is spectral. Okay, so we have already seen that atomic C-star extreme points are spectral. So slightly roundabout way, we show it for finite dimensional H. Now we come to completely positive maps. So here the setting is compact Hausdorff space, not general measurable space, just a compact Hausdorff space, and UCPCX. So unital completely positive maps on the algebra, the C-star algebra of continuous functions on X with values in B of H. So again, we have to define what is C-star convexity. So here is the definition, which if you remember the definition for POVMs, it is exactly the same thing, just that the measure has been replaced by the CP map, right? So you have C-star convexity summation Ti star phi t, each phi is a unital completely positive map. And the same way you have the definition of C-star extreme points. Okay. So this was the original definition of C-star extreme points. Once again, you should note that each of these, when you have proper convex combination, each TIs are invertible, then this phi should be unitarily equivalent to phi. Okay, like this. You don't say that phi equal to phi. Okay, so this was the definition of Ferenczi and Moritz. So, well, how do we prove theorems here? We just see the correspondence. So you have to see the concepts match. So a normalized regular POVM mu is C-star extreme here in the set of regular POVMs if and only if the corresponding UCP map is C-star extreme. Okay. So C-star extreme things match. C-star extreme of POVM means C-star extremity for UCP maps. The usual extreme point for POVM would go to extreme points of UCP. Okay. So the correspondence respects this C-star extremity as well as extremity. Okay. So that's a theorem, not difficult, but it's a theorem which helps us to transport results from one domain to another. So here for CP maps, the things which correspond to spectral measures are the star homomorphisms. So they have already proved, Ferenczi and Moritz, that every unital star homomorphism is a C-star extreme point. Okay. So now we want to go the other way around, but as I said, in general, it is not possible. With some good situations, it is possible. So let A be a commutative unital C-star algebra with countable spectrum. So here is a condition with countable spectrum. And then you take a UCP map, then phi is C-star extreme if and only if it is a star homomorphism. Okay, so the assumption here, of course, I'm only talking about commutative C-star algebras now, but the crucial assumption here is the countable spectrum. Okay, which corresponds there to taking countable measurable space. Okay, we apply this theorem to one special case. The C-star algebra generated by a single normal operator. So you take your Hilbert space H, take a normal operator there, and then look at the C-star algebra generated by that normal operator. So let n belonging to B of k be a normal operator on a Hilbert space K with countable spectrum. Okay, once again, we have this condition of countable spectrum. The spectrum of a is assumed to be a countable set. So look at the unital C-star algebra generated by n. Okay, which means you take powers of n and n star and their linear combinations, and okay, you take polynomials with n and n star. Okay, and take the norm closure. That is the C-star algebra generated by n. The smallest C-star algebra which contains n. Okay, smallest unital C-star algebra which contains n. take any closed subspace H of K, and we look at this CP map, the compression of T. So you take any, so the C-star algebra under consideration is the C-star algebra generated by N. Since N is assumed to be normal, so N commutes with N star, so that means this is a commutative C-star algebra. So on this commutative C-star algebra, we define this map, phi of T is the compression of T. Okay, you just compress, so you just cut off T to a smaller Hilbert space. So that is the compression map. So that is a unital completely positive map, easy to see. If you take identity here, you get the identity of H, and positivity also easy to see. So the following are equivalent. So the theorem, it's a C-star extreme point here, if and only if it is star homomorphism, if and only if H is an invariant subspace for N. So N leaves H invariant, that is N of H is contained in H, or H is a co-invariant subspace, so that means H perp is invariant for N. Okay, the orthogonal complement of H is invariant for N, or H is reducing subspace for N, so which means it's both invariant as well as co-invariant. Okay, all these are equivalent. But you should remember, we had one assumption here, crucial assumption, that it has countable spectrum. Okay, so it is not true otherwise. Okay, so in general, an invariant subspace need not be co-invariant. Okay, here they are all equivalent. Okay, so here is the example to see that that in general invariant doesn't mean co-invariant. This is a Hardy space example. And consider the Hardy space H2 on the unit disk. Okay, so what is this? So these are functions summation an z to the power n, where summation mod an square is finite. Okay, so it is like small L2, but you put it in the function space. So summation an z to the power n, functions of that kind, where summation mod an square is finite. Okay, same the L2, that norm you put. Okay, so you define from the continuous functions on the circle to bounded operators on H2. How do you define? The multiplication by F compressed to H2. Okay, so multiplication by F defines an operator on this L2 of the circle with respect to the usual Lebesgue measure. Okay, and then you compress it to H2. H2 is a subspace of this. Okay, so just the compression map, which is the same example like the previous one, is exactly like this. Okay, the same kind of example, but it's just that the spectrum is the circle. Okay, is the same kind of example. So here MF denotes the multiplication by F on L2 of the circle. It is known that this phi is a C-star extreme point here. I think it is due to, again, by Faranik and Morans, and it was shown to be an extreme point earlier by Arvesen, the usual extreme point, though it is not a star homomorphism. Okay, so here is an example where you have an example of a C-star extreme point which is not a star homomorphism. The corresponding thing you can do it in the POVM language, okay, on measurable sets and that. So then you see that you get an extreme point, C-star extreme point, which is not a spectral measure. Okay, so that kind of example also we get from here. So as I said, it is not a very exotic thing. It's just, there's a standard example where it's not a star homomorphism, but it's C-star extreme. Okay. So what can you get here in this setup? So you can. So I spoke only about limited things, some main results. So the paper has many other things about measurable equivalence and many other things. Using those things, one can, from this example, I can transport it to many other examples, many other subsets of the disk of the plane. So here is the general thing. AB is separable commutative unital C-star algebra with uncountable spectrum. So earlier we dealt with countable spectrum. We take uncountable spectrum. So then it is always possible to get a C-star extreme point which is not a star homomorphism. Okay. So nothing special here about the circle or the disk. You can do it in general. As long as the spectrum is uncountable, it is possible to get an extreme point which is not a star homomorphism. Of course, this theorem is not very satisfactory because you would have been happier to describe all such extreme points. We are all just saying that there is at least one extreme point which is not a star homomorphism. How do they look in general? That one would like to know. Here is one open problem. So, which looks simple, but we don't know how to solve it. So, our C star extreme unitas completely positive maps on the C star algebra L infinity. You take the sequence space L infinity, the sequence bounded sequences, which is a C star algebra, unital C star algebra. So on that, to some B of H, are the C star extreme points are always star homomorphisms. Is it true? We don't know. Okay. What is the spectrum? The spectrum of L infinity is the Stone-Zec compactification of natural numbers, and this space is not metrizable. So whatever we did before is most of it is not applicable. So we don't know how to handle it. That is the problem. So we would very much like to have an answer to this question, because I think once we know this, we will know how, like, if the answer is no, like, then we'll know how these other extreme points look like, and maybe it will help us. Okay, so it will help us to go further. So this is a sort of, we think it's sort of typical example to understand. Okay, so thank you. I may have finished a few minutes early, but it's good to have some questions. So thank you for your patience.
Raja, can you hear me?
Yes.
Yeah, there are questions in the chat box. So Dr. Hussain has sent some questions. You check your chat box.
Chat box, I don't. Oh, okay, I see now. Okay.
There are quite a few.
Yes, yeah.
Once you are done with that, we have more questions from the audience.
What is the most general situation where usual extreme points and C star extreme points of POVMs coincide? Well, we don't know the answer. Actually, typically it is not, because even for finite sets, there are extreme points which are not spectral. Okay, so typically POVMs are, the C star extreme points are special. They are often spectral, whereas the usual extreme points in general are not spectral. So most situations this will not happen. The extreme points, there will be other extreme points other than the spectral. Okay, like only if you have 2 points in the continuous function on 2-point set or 1-point set, that would be the case. So most other cases, the C star extreme points should be a smaller set than the extreme points. But we don't have a theorem. Actually, if in the general situation, we don't even have a theorem that a C star extreme point is automatically extreme. That kind of theorem also we don't have. Okay, the second question, do we have Crane movement? Oh, that's a nice question. Yes, the answer is yes. So if you look at the preprint I cited in the beginning, it has that kind of results. I didn't talk about that Crane movement type theorem, but it's there, which essentially says that using these spectral measures, you can, using their convex combinations in suitable topology, you can approximate everything else. Yeah, so answer is yes to the second question. No to the first question. In most situations, it is we don't. They are not equal, and we don't have a general answer.
So, aren't there more questions there in the chat box? That's all that you have there. Yeah, yeah. Yo, so then Arun here has a question for you.
Yeah.
Hello.
Yeah.
Sir, can you hear me?
Yeah, please.
So the set PHX,
Yeah.
does that set has the structure of matrix convex sets?
Matrix.
So yeah, instead of H, you take Cn and you vary like. So are you familiar with matrix convex sets?
You mean X you take to be Cn, is it?
Yeah, and you vary n. Like there is a generalization.
Okay. Matrix structure.
Yeah.
Yeah, I suppose you can do it because you can do it for CP maps, but I don't know whether it will give you something new. Because the thing is that it corresponds to CP maps on a commutative sister algebra. No, so there you don't get anything extra by looking at matrices. So it's unlikely that you get something new. But
Okay.
Yeah.
So that's it. Yeah.
Thank you, Raja. Are there more questions? If not, let us thank Raja for his nice talk.
Thank you. Thank you.
See you sometime again here. You are the first speaker of the first conference here. So we want to see you again here once the lockdown is over and such. Right?
Yeah, I hope I can come sometime. Let us see. It all depends upon COVID.
Okay, bye-bye.